Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 14th video lecture. And we're talking about topology, and I want to start off with a definition. I want to start off with a fact. And it says, if X is a metric space, with metric d sub p cubed, and y is a subset of X that is non-empty, then y with this metric is a metric space. That is, we're restricting to metric to just the elements of y, and with that restriction, y with that metric becomes a metric space. Okay. As a definition, we let X be a metric space and Y, here's non-empty, be a subset of X then E, which is a subset of Y, is open relative to, or it says with respect, or relative, with respect to Y, okay? I'll say relative to Y. If for each P in E, so for each element in E, there exists an R greater than 0, such that if the distance between P and Q is less than R, and Q is in Y, then that forces Q to be in E. So that's what it means for E to be open relative to Y. This is kind of the idea of P being an interior point. It's not kind of, it is the idea of P being an interior point of E relative to Y. That is that you can get a neighborhood that if you look at a neighborhood of P, that if you look at its intersection with Y, then that's totally contained in E. We'll look at a quick example. We'll let R be a metric space with the distance between X and Y being equal to the absolute value of X minus 1. That's the usual method. So we consider a subset of R, which is R is our X, and here we consider Y equaling to the interval from -1 to 3, where we include -1 but not 3. And then let E be equal to the interval from -1, including -1, to 1, but not including 1. Then E is open with respect to Y, but E is not open in R. So essentially, every point of E is an interior point with respect to Y, but it's not an interior point with respect to R. And the reason is if we think about this, here's the real number line, and we think about here's Y, it goes from -1 to 3 in this fashion. And we're just looking at this part of it. Here's E up to 1, just this part of it. Then if you give me any point in E, okay, there exists an R such that, I'll say this radius, at this point, such that if you give me any point in here, okay, that's also in Y, so it's in that neighborhood and also in Y, then it's going to be in E, and every point that's in here is also in Y. But what happens for -1, if you give me some neighborhood about that there exists this neighborhood -1, take this one, okay, I'm drawing right here, and if you look at out of that neighborhood, just the points that are in E, you get this. Okay? The points that are in Y, I should say, you get this. This part, the right-hand part of that interval. Just the part that's in Y. And then that forces those numbers to also be in E. So that's why -1 is an interior point of E with respect to Y. Okay, I'd like to look at a theorem. Here's what it says. It says, suppose Y is a subset of X, which is a metric space. A subset E is open relative to Y if and only if E is equal to Y intersect G for some G that is open in X. Open, I'll say subset of X is an open. So this is an if and only if statement. So we'll have two directions. We'll start off, first of all, even with any directions, let's let Y be a subset of X, which is a metric space. Okay, we're also going to let E be a subset of Y. Now, here's this direction. Suppose E is open relative to Y. Okay. We want to show that E equals to Y intersect G for some G that is an open subset of X. Okay, so here's what we did. For each P that is an element of E, there exists an R sub P greater than 0, such that for all Q in Y, with their distance from P to the distance between P and Q is less than RP, and for all Q, Q will be an element of E. Okay, we're going to look at some sets then. Okay. So what we're going to do is we're going to let B sub P be equal to all the Q's that are in X, such that B sub PQ is less than RP. Okay. Now, we're going to let G equal to the union of all the P's in E of B sub P's. Okay. Now, I want you to notice that what B sub P is, B sub P is a neighborhood of P, okay? And so it's open. And so when you union a bunch of these open sets, an arbitrary union, you're going to get an open set. So let's write this down. Note B sub P is open in X as B sub P is a neighborhood of P. So G is equal to this union, arbitrary union, is open. It's open in X. Okay. Now what we need to do is show that that E is contained in Y intersect G, and that Y intersect G is contained in E. Okay, so here's what we'll do. We'll let P naught be an element of E. Okay. Then P naught is definitely in V sub P naught, okay, as the distance between P naught and P naught is equal to 0, which is going to be less than R sub P naught, which is bigger than 0. Okay. So that means that P naught is in this union. So P naught is an element of the union of all the P's in the V sub P. Okay? Now remember, P naught is an element of E, and so E is a subset of Y. So that means that P naught is going to be an element of Y. So from this last line here, and what I just said, that P naught is an element of Y, what we get is that P naught is an element of the union of all the P's in E of V sub P intersected with Y. And that union was, and that's because, as E is a subset of Y, as we said. So that tells us that E is a subset of G intersect Y, because this is G, okay? Now I took an arbitrary element of E, and I showed it was in the right-hand step. Now we have to go in the other direction. So here, if we let Q sub 1, other direction of the equality between the two sets, be an element of G intersect Y, what we're going to do is show Q1's in E, okay? So what this says is Q1 is an element of Y, and Q1 is an element of the union over all P's in E of VP. So what does it mean to be in this union? There exists, let's say, a P sub 1 element of E such that Q1 is an element of V sub P1. That's how you get to be in this union. So what does it mean to be in V sub P1? So that means that the distance between Q1 and P1 is less than R sub P1. Okay? And we know that Q1 is an element of Y. Okay? It's in that intersection. So, what that gives us is that Q1 is an element of E since E is open relative to Y. Okay? So P1 was in E. That's what we're thinking about. Okay? And so from the definition of what it means to be relatively open, for E to be relatively open in Y, we get Q1 has to be in E. Okay, so that's showing that E is equal to this G intersect Y. Let me write that down. That's one part of the proof. Okay, now we have to go in the other direction. So we let E be equal to, let's say, some G intersect Y, where G is open and open, let's say, is an open subset of X. Okay? What we want to do is we want to show that that E is open relative to Y. Okay? Okay. So how are we going to do that? Well, we're going to let Z be an element of E. We want to show there exists an R sub Z, which is greater than 0, such that if, I'm just using the definition of what it means for E to be relatively, to be open relative to Y. So we want to show that there's this radius, R sub Z, such that if Q is an element of Y and the distance between P and Q is less than RZ, then Q is an element of E. That's what we want to show. Okay? Okay, well, since Z is an element of E, and E is equal to G intersect Y, then I said Z is an element of G. That has happened. And G is open, so this means Z is an interior point. So there exists an R sub Z greater than 0, such that this neighborhood n sub R of Z, which equals to the set of all, let's say, Q's element of X, such that the distance between Z and Q is less than RZ, that this set, okay, is contained in G. That's because G is open, so Z must be an interior point. Okay? So, for every Q, such that the distance between Z and Q I made a mistake back here. My notation. I want to make this correction, okay? I'm sorry to stop. But here, what we want is DZ, the distance between DZ and Q to be less than RZ, okay? So make that change. I had P here, that was wrong. Okay. So it's that DZ and Q is less than RZ. So for all Q's that have that, and Q being an element of Y, then Q will be an element of E. And that's what we wanted to show. That's it. The reason that that is true, of course, is that this Q is going to be contained in G, okay? And it's going to be contained in Y. And so that's what it means to be in E. So that's the proof. Okay, I want to look at kind of a definition as opposed to the interior point or openness relative to Y. We want to do that in terms of closeness or limit points. So let me give a definition for limit points relative to Y. Here's the definition. Let X be a metric space. Let E be a subset of Y, which is a subset of X. A point P is said to be a limit point of E relative to Y if P is an element of Y, that's something that's important, and for every R greater than 0, there exists a Q that's different than P. It's an element of E. Okay? So Q is an element of E, is what I'm saying. With the distance between Q and P is less than R. I'd like to look at an example. So, as an example, let's look at E is going to be equal to the interval from -1 to 3 in this fashion. Notice it's a subset of -1 to 6 in this fashion, which is a subset of R, which we'll think of as our metric space with the usual topology. This is our Y, and this is our E here. Okay? Then, what I want to tell you is, just an example, is -1 is a limit point of E, okay, in R. But -1 is not a limit point of E relative to Y. Okay. Now, I want to give a definition. So it says E is relatively, or E is said to be closed relative to Y if E contains all of its limit points with respect, I'm going to put it right here, to Y. Okay, that's pretty much all I wanted to say about these limit points relative to Y. We're going to move on to another topic called compactness. Okay, we need a preliminary definition for that. And so here we start off with by an open cover of a set E in a measure space. We mean let's call the metric space X, just insert this. We mean a collection, we call them G sub alphas, alpha's element of A, such that G sub alpha is open in X, and that's true for every alpha element of A. And E is contained in the union of the G sub alphas. So that's what needs to be an open cover. Let's look at some examples. Here's the first one. So I'm going to let E be equal to 0 to 1, where 0 is included but 1 is not. Then, if you look at this collection, intervals from -1 to 1 minus n. N is an element of the integers. That is an open cover of E. 2. Another example. If we let E be equal to the closed set from 0 to 1, then the set that looks like, the collection of sets that look like 1 over n up to 2 is not an open cover of E. Not an open cover or covering of E. The reason that this isn't an open covering, it's open, all of this collection is open, but you never get 0. Okay, so the E is not in the union of these guys. And then I want to do a third example. Here we let E be equal to 0 to 50. Then the collection of -1 to n, as n runs from 1 to infinity, is an open cover. Of E. Okay, so that's some examples of open covering. But what we're going to be interested in is sets that when you give an open covering to me, that a finite collection of that open cover will also cover K, or cover that set, and I call it K. And so those types of sets have a special name they're called compact sets. So let's write out that definition. A subset K of a metric space X is said to be compact if every open cover of K contains a finite subcover of K. That's what it means. We'll look at some examples of that, or at least I'll state some. So as examples, first one, I want just to tell you that 0 to 50, this closed interval, is compact in R with the usual measure. And this will be shown, be proven later. 2, this set 0 to 1 in this fashion is not compact. As here's an open cover for it, one we've already seen, -1 to 1 minus 1 over n. Okay? But this open cover has no finite subcover of 0 to 1. Okay, we can talk about compactness relative to a sub set of a metric space Y. Let me write up that definition. So here it is, definition. Let K be a subset of Y, it's a subset of X, and X is our metric space. Then K is compact relative to Y if for every collection G sub alphas which are open relative to Y. Okay, so the G sub alpha is open relative to Y. That form an open cover of K contains a finite subcover. So it's the type of definition that you would expect. We're just restricting ourselves to Y. And then I have the theorem that I want to prove about such things. Namely, suppose K is a subset of Y, it's a subset of X, X is a metric space. Then K is compact relative to Y, relative, let's say, to X, if and only if K is compact relative to Y. This is an if and only if statement. Proof, let's let K be a subset of Y, be a subset of X, where X is a metric space. Okay, so here's got two directions. So let's assume, suppose K is compact in X. Okay? We want to show that K is compact relative to Y. So how do we do this? Well, what we do is we let G sub alpha be a collection of open sets relative to Y okay, that cover K. Okay, we want to show that there's a finite collection within this G sub alphas that will also cover K. Okay? That is, we want to show G sub alpha has a finite subcover of K. Okay, well, here's what we know. We know that the G sub alphas are all open relative to Y. So we know that G sub alpha then must be equal to Y intersect V sub alpha, where V sub alpha is open in X. Okay? And that's what, from the fact we proved this lecture, that if you're open relative to Y, you have to look like this type of set. Okay. Okay, so the V sub alphas then form an open cover of K in X. So that's what we have. So since K is compact in X, there exists a finite subcover of the V sub alphas, say b sub 1, b sub 2, up to b sub n of k. So that means that k is a subset of this union as I run from 1 to n of the b sub i's. Okay. So k is going to be a subset of the union as I run from 1 to n of the b of sub y's, I should say, intersected with the b sub i's. Okay. Okay. And so that means that k is going to be a subset of the unions as I runs from 1 to n of the g sub i's. So that says that g sub 1 up to g sub n is a finite cover, finite subcover. Of k with respect to y, or relative to y. Of the g sub alphas. So that's one part of the proof done. Now we're going the other direction. We let k be compact relative to y. We want to show that k is compact in x. Okay, well, since k is compact relative to y, then what we could say, then every g sub alphas, this is something to remember, which is a collection of open sets relative to y, has a finite subcover for k. Okay, so what we'll do is we'll let b sub alpha be an open cover of k in x. Okay. Then, if you define the g sub alpha to be equal to y intersect b sub alpha, that this collection of sets forms an open covering of k relative to y, Okay, so since K is compact relative to Y, that means that only finitely many of them are needed. So that means that K is a subset of some finite number of these Y, I running from 1 to n of the G sub i's, I should say. So that gives us that K is going to be a subset of the union as I run from 1 to n of the V sub alpha. So only finite V sub alphas are needed. Okay? And that's the proof. Oops. Okay, ladies and gentlemen, that should be enough for this video lecture. Thank you very much.